addressing one of the important aspect of any refinery, petchem, or any chemical complex, that innovation in utilities and power systems. See, in terms of energy, if you go, utilities are one of the major consumers of total feed, which is going to be there in a complex. If you take even refineries, even petchems, or any chemical plant, utilities are one of the major consumers of power. Say very rough range, if we say, it goes into the range of say 20 to 30-35%. So there is tremendous scope in it to improve the energy consumption or energy number of any complex if we optimize the fuel or feed consumption in the utilities part, whether it is a firing of the burners or the reformer or the boilers, where there are various utilities like power generation systems, cooling water system, instrument air. So these there is tremendous scope in the same, which wherein we can improve the energy number, energy optimization can be done. So today we have four eminent speakers were planned in this session today. I believe there are three of them have arrived today, and I'll ask my co-chair, Mr. Naveen, to introduce the speakers and go ahead with the session. Over to Mr. Naveen, please.
Thank you, Verma ji. It's really nice to have my co-chair as my colleague also in the company. This topic is very relevant because I have experience working in the operations and especially the sections of utilities and power. So this session is very close to my heart. And if you see last in the period of energy transition, the energy conservation aspect, especially in the utility sites, is very important. In addition to energy optimization strategies which are being adopted across the complete value chain in industry, we are facing some current challenges with respect to energy transition. These current challenges, including the sunsetting of coal power plants, then there is a rise in the DERs, that is distributed energy resources, micro generation and non-utility providers, the need to account for dynamic supply and demand, and acceleration of cooperates for net zero pledge. In the recent budget also, Prime Minister has given importance to the renewables with respect to 1,000 crores. Yeah. आवाज नहीं आ रहा. So the current budget provisions, which recently Prime Minister, this Finance Minister announces regarding 10,000 crores in 2024 budgets for solar power schemes. Wind power allocation has been increased to 930 crores in these budgets. Then there is a viability gap funding. So there is a high impetus on the uses of non-fossil fuel power generation and its effective utilization. Considering these aspects, I think our eminent speakers has given some nice ideas and presentations. So I think we will ask one by one to be at on the stage to present the ideas in front of the eminent. So I first call Mr. Umang.
Yeah, as per the names listed in the screen, we invite Mr. Umang Nagpal to begin their first presentation. Just before we start, we have roughly 15-16 minutes for the speakers, each speaker, and at the end of all three sessions, all three speakers, we'll have a question answer round. So, to the attendees, you can keep noting your questions, queries, and at the end of session, you will have around 15 minutes time, maybe little less, 12 minutes for the question answer section. So, over to Umang, please come to
Just
the
a
dais.
brief intro of Umang. Umang
Yeah.
has done his graduation from IIT, ISM, Dhanbad, and is a geophysicist and working for last 1 year with ONGC.
Thank you, Honorable Chair members, for the introduction. Uh, Good morning, everyone. My name is Umang Nagpal. I joined ONGC last year as a geophysicist surface. Today, I would be presenting a small exercise on predicting electricity consumption and generation in our country. So I'll start with a small overview about it. As we all know that Indian Electricity Center is currently undergoing a substantial transformation driven by the changes in the electricity mix, which is influenced a lot by the policy focus and climate change policies. So recognizing the energy production is very important to align with the demand of what coming up so that we could invest strategically in the investments in the energy sector. This study over here employs a multilinear regression model to establish a significant relation between 12 key parameters from agriculture, industry, and other sources so that we could predict what electricity demand would be in a particular year. Moving forward, we would use time series forecasting using random forest and neural network to see how or what capacity of electricity we could generate to match the gap. By combining these models, this study would provide a comprehensive approach to independently forecast electricity generation and consumption in our country. Now, this somehow gives us an idea of what an optimal solution would be so that we could reduce the demand shortage and reduce our reliance on fossil fuels. So, in the recently organized United Nations Climate Change Conference, the India government presented their 5 goals called Panchamrit. So we plan to focus on establishing and increasing fossil fuel capacity by 500 gigawatts by 2030. We also aim to meet 50% of the energy's demand by non-fossil fuels and hence achieve net zero by 2070. So if you would see on the left bottom, there is a graph, an animation which is showing the increase in global warming temperature of the entire world annually. And it is evident that in the last 2 decades, the temperature has significantly increased. India is perhaps almost the 3rd highest greenhouse gas emitter. So it is high time to reduce carbon emissions and reduce our reliance on fossil fuels, which, if not done, can cause India to lose 2.6% GDP annually. And since the agriculture productivity is already declining, prices of cereals are increasing, this could make India to have a higher poverty rate of 3.5% by 2040. We know that cities like Surat, Mumbai, Kochi are already prone to coastal flooding and there is an estimate to lose around 4 trillions if not done. So why do we model electricity demand? So we have to understand that energy production and its availability directly influence future production imports availability. And hence, it has a significant impact on the country's economy. On the top left, we are showing the production of electricity by commercial sources, which has increased from 14,000 petajoules in 21 to 16,000 petajoules in 2022. It has a CAGR of 8.82%. It is evident by looking at the graph that coal accounts for majority of the electricity produced in India. Now look at the graph which is showing total consumption of values. We can see that around 30,000 petajoules of energy were consumed in 21, while around 33,000 petajoules was consumed in the last year. It has increased at a CAGR of 3.9%. So the increase in rate of consumption of energy is more and greater than what we could directly produce in the country. So there is a gap, right? Energy, as on March 2023, India had around 4 lakhs megawatt of installed capacity, out of which coal accounted for 50%. But surprisingly, coal accounted for 73% of the total generation in India. Now, see, I mean, it makes sense that coal, fine, is the leading producer in India. Why? Simply because it is highly abundant in nature. It has a smaller gestation period. It is the setting up of a coal plant require less amount of money. Now, I would like your attention to the left graph over here. We can see that the amount around 1,000 million tons of coal were consumed in India in 2021, and it is growing at the rate of 13%. Around 780 million tons of coal was produced in India, which is growing at a rate of 8.67. So we are producing less coal than what we can eventually consume, and it is growing at a lesser rate. So how is the demand energy deficiency solved? Solved by imports. That is what we need to counterbalance. So to maintain the energy balance and finding the optimal generation mix becomes very important. Now, by running our model that I will show in the present slide, we aim to find that right number or golden number through which we could reduce our dependence on coal and not at a cost of a national electricity blackout. Now we are focusing to reduce the coal imports. Around 3.85 lakh crore rupees was spent on importing the coal in India. We need to decommission the inefficient coal-based plants. The Indian government has already planned to retire 50 to 100 megawatts of coal which are not efficient enough. Now we need to increase the already existing coal capacity, and we also need to increase the renewable capacity in our country, which we have already planned to do by 2030. Now, before modeling the electricity, we need to understand and quantify the parameters on which electricity generation and consumption is dependent. On the left, we can see that the electricity generation has increased from somewhere around 700 billion units in 2009 to 1600 billion units in 2023 at a CAGR of 5.7%. Now, in order to meet COP26 guidelines, it is important that the coal graph should decline because renewables are already increasing and it could compensate for that. Renewables are increasing at a rate of 17%. Solar, I think, grew up to 45% in the last year. Now look at the electricity consumption in India. We can see that electricity consumption increased from 600 billion units to 1400 billion units at a CAGR of 6.1%, which is faster than what electricity we are generating in India. Industrial sector accounted for a majority of the electricity consumed in India, somewhere around 42%. It is growing at a rate of 7%, followed by domestic and agriculture sector. Now, according to a study in CIA 23, it is possible. I mean, achieving the goals would be only possible if non-fossil fuel contribute to 64% of the total electricity generated. The table over here shows the planned and projected installed capacity in India. Now look at the solar graph. It has increased from 13 to 37%. While coal and lignite should remain more or less same, and we should decline its share to 32%. So what we are expecting or what we hope through the model is that we could somewhere decrease what we were generating through coal was 73, decline the share from 73% to 50% and increase the solar share to 22%. Now this mind map over here shows us the drivers of electricity demand that we are using in our model. Steel and cement production is increasing through the industrialization. Policies like National Manufacturing Policy, Make in India, Pradhan Mantri Suryodaya Yojana, which was recently launched, requires a lot of electricity. Agriculture, good yield is possible by rainfall, irrigation facilities, pump sets, which are somewhere energy-wise expensive. We are building EV sales are happening. We have to build EV infrastructure, rail track growth, railroad electrification around. We hope to achieve 100% railroad electrification in 2024. So these things would increase the demand of electricity in coming years. Household sizes, applicants type, Pradhan Mantri Awas Yojana, around 100 million households are planned. Now look at the demand of electricity that would be coming from there. Population growth, GDP, hydrogen policy are some of the factors which we have taken into account in our machine learning model. These were the parameters we have chosen, and the data set has been created using the values of these parameters from 2012 to 2023. Electrification of rail network, pump sets energized, India's GDP, AC market size, annual rainfall, India's average household size. Now you would observe one thing, average household size is decreasing. Why? Because earlier we used to live in big homes. Now the migration is happening and we have dwelled into smaller homes. Smaller home means more number of electrical appliances in home. Around last year only AC has increased 66%. Crude steel production, length of transmission line, India's household well, EVA registration, annual yield, and cement production. One important thing, if you all can notice over here, is the downward kink is coming in many of the graphs. That is because of the pandemic, COVID pandemic. So if we run our model, we have to make sure that our model picks the downward peak also. because it is important for our model to have a ground truth. Now, using these parameters, we prepare a data set. We split the data set into 80-20 ratio to train and test. Around values from 2013 to 21 is used for training. And the model, we use a multilinear regression model because somewhat the model was linear. And then we test the model to predict the electricity consumption for year 2022 and 2023. Now, on the heat map on the left, we could see that the parameters we have chosen somehow has some inherent correlation between them, and it becomes very important to remove the highly correlating parameters so that our model doesn't overfit. Okay, so we use recursive feature elimination over here to drop the redundant values based on VIF. The plot in the center, if you would see, shows the comparison between the actual electricity consumption and what our model is predicting. Now, our model works very fine on training data set, and it is also able to pick up that downward peak we talked about. So the model is reliable, but somehow the model lacks some improvement on the test data set. Now, why it is happening is, it could be that the model is trying to accommodate the lost linear growth, or the model is trying to behave in a fashion if there would have been no COVID. So it is trying to mimic, because COVID was an exception for it. Yeah. So the correction or the improvement to this could be done if we could have more data points at the end of the line. How would that be possible? If this study would have been done in 2026 or 2027, at least we would have some parameters and data points after COVID. So that would help change the slope of the graph, the slope of the predictive curve, because right now it's much higher. The slope of predicted is much higher than slope of actual. So we could somehow try to match it to the actual consumption values. The model accuracy was 82.26 Hertz. The actual electricity consumption value for 2022 was 1255, for 23 was 1327. The predicted values came out to be 1360 and 1607 kilowatt hour per capita, respectively. Now, we are in that position where if you would give me the dependent parameters which I talked about, that could also be the known target set by the government. My model could predict the electricity consumed in that particular year. Now you may ask, why was so much analysis done in the previous slide? Is it even necessary? But you have to understand that machine only understands number, and it is our responsibility to make sense of it, interpret and understand the ground truth. So, for example, if the policy thinkers plan to reduce the dependency of coal by X%, and by our model, we can understand that, okay, fine, Y is the amount of electricity that would be consumed in a year. Then our focus should directly be upon what is the electricity generated in a year, what I could really produce, so that I could match the demand of the country. So it helps a lot in planning. Here we talk about electricity generation. In this exercise, we forecast electricity generation using time series dataset extracted from the grid controller of India's daily reports, PDFs, from 2017 to 2023 in million units. So after we prepare a dataset, we do a stationary test using ADF, and we get a p-value of less than 0.05, which is in good regard. So subsequently, we use two different models, random forest and neural network, to compare their performance by predicting the electricity generated in 2023 and checking their mean absolute error values. So this is the results from random forest from 2017 to 23 from 5 different sources: thermal, coal, gas, nuclear, and hydro, and renewables. So the dataset here was divided into 80-20. Now finding the optimum hyperparameters in random forest becomes important, like the depth of forest, number of decision trees. So we used a grid search method where the parameters which were giving us the least error in the model were chosen, and then they were used to train the model set, train the dataset. The errors for different sources have been mentioned on the table on the right over there. The actual electricity generation value for 23 was 16 to 4 billion units. Our model predicted to be somewhere 1599 billion units. Now, one peculiar thing, if you would observe over here, is that our model for thermal and this nuclear and renewables, there is somewhere an upper bound. if you will see, there is an upper bound over here, there's an upper bound over here, there's an upper bound. So this is like a constraint. The model has become biased. I think it's trying to just take the highest peak of what it has learned in the training data set. So the results were not that good. So we tried to overcome this problem by using neural network. This is the result which we get through the neural networks. And if you would see, the neural networks work really good. There is no, it is easily able to pick up the up and down peaks. There is no constraints over here as we saw previously. So in order to prepare the data set, we try to add lags in the data so that we could create multiple subsets of the training data set. Now, one important thing was also here to catch the short-term temporal resolution. Adding lags is really suggested because hydro would increase more in summer and would go down in winter. So this was done. The errors are mentioned on the table there. The electrical electricity generation we discussed was 1624, but our model predicted was 16.12 billion units, which is
Umang,
better.
You have 1 minute left.
Yeah, I'm in.
Please.
So, in order to conclude, I'll say that it is an intricate task to forecast electricity demand, and with rapidly evolving economics like India, it is very challenging. Recognizing the existing shortfall in production, we propose a strategic approach involving capacity addition, reduction in coal, and a sustainable demand in renewable energy production. Our model, the benefit of the study is when we are using this as an independent tool and finding the optimal energy mix in both case, high renewable scenario and low renewable scenario, case to case, and depending on the government frameworks and policies. While the standalone application for this modeling have some limitations, and we are doing some ongoing work on it to improve its scope and utility. That's all from my side. If any one of you is interested to use our model and data set, I'll be very happy with it. So you can scan the QR code and I'll add the notebooks with you. That's all. Thank you.
Thank you, Umang. You presented a very good, unique model to predict the power demand and different scenario discussed. You made a good critical remark on the coal. So that let's see, we can at the end of session we'll say something on that. So for the next session, I'll ask my co-chair to invite the next speaker.
Thank you, Umang, for very excellent presentation you have done, especially using the modern tools. And one important aspect is that it's a predictive model, so it will help definitely for strategic planning. Yeah, we will have a Q&A session at the end of this all speakers. Now I request Surbi, please be on the stage for our presentation. Ms. Surbi is an instrument engineer and post-graduation in marketing and HR. She has around 17 years of experience, presently working with Emerson for last 8 years. Currently, she is leading Asia Pacific Renewable Energy Business Development and Global Renewable Prospects and Tendering Leader for Emerson. I welcome Surbi and all the best for the presentation.
Yeah, thank you. Thank you for the introduction and a very warm welcome to all the audience sitting out here. And I'm Shubhi Goel, and I'm going to present a case study on large-scale solar PV automation solution deployment. So this case study is about Lodestone Energy, and Lodestone Energy is a growing solar PV power utility company based out of New Zealand. And I'm going to talk particularly on the phase 1 implementation, where we have supplied our solar PV power plant controller and SCADA solution for 5 sites which were geographically distributed and into the northern side of the New Zealand. So with using the automation solutions provided by us, Lodestone Energy was able to attain the operational excellence, and they will be able to achieve the CO2 reduction to the tune of 5,300 metric tons per year. So I'm going to explain more on the solution. And here I would like to take this opportunity to introduce my company, Emerson Automation Solutions. We are big giant in the power generation space. Globally, we have 1400 gigawatt of the power generation, which is getting automated on our control system platform, be it traditional power or renewable power. And out of that, 76 gigawatt is what we have been doing in the renewable space. So renewable is very core for us in our business, and we have been doing solutions across solar, wind, hydro, biopower, waste to energy, as well as geothermal power plants in the renewable, and we are doing the pilot projects for green hydrogen as well. Okay, so that was quick on the company profile. Coming to the Lodestone Energy. As you can see, this is in New Zealand, and we were engaging with this customer, which is a power utility company. It is called the pre-feed study, where we engaged almost a year back before we received this contract. And we were doing the front-end engineering, where our team worked along with Lodestone and designed the power plant control philosophy. We were engaged in designing the, the plant automation network. We were doing the interface management, where in case of solar, SCADA and PPC, we have to interface with various equipments and devices, be it PV inverters, be it your weather monitoring systems or your power quality meters, or doing interface with combiner boxes, and also on the substation side, where with various electrical intelligent devices and relays. So we were designing the complete network philosophy, doing the alarm management, doing the graphics, reporting, and also designing the FAT and SAT procedures. So that was part of the front-end engineering, where we engaged with customer and design the whole plant philosophy. And after a year, we awarded this contract for the feed study, and later on we got the supply order, in which we supplied the hardware, software part of the PPC and SCADA. So apart from the front-end engineering, if you talk about the technical solutions, so we have provided the power plant controller, which is the grid interface controller here, which is sitting inside the main control room and doing all the main controls which are related to the grid. So you have your grid transmission operator, which is providing the set point from the grid RTU, and we are defining all the control logic, how to dispatch that set point to the different PV inverters, which are the generators in the solar PV plant, right? So we are doing that. Apart from that, we are doing all the software application suite, including the scalable SCADA, doing the forecasting model as well. So as we heard from Mr. Umang in the previous session, so in this project, we have also designed the forecasting model, in which we are able to generate the power forecasting, which is provided to the grid operator at a period of 15 minutes schedule. Also, we are doing solutions on the CMMS, which is the computerized maintenance management system, which is related to how your assets are going to behave, and it is part of the prediction maintenance model. So we are kind of taking all the data from the assets, like inverters or switch gears or weather stations or any equipments which are there in the field side of it, and we are doing the prediction analysis. Or maybe the PV string monitoring, so that is again very critical, and if any string going bad, so our module is able to detect that in advance based on the pattern recognition, and inform to the operator in the form of diagnostics and alarms. So that was also part of this solution. And also we are doing the PV performance models, which is where we have defined almost 35 key performance indicators for the PV plant, which relates to your performance calculation, your efficiencies of inverters, efficiencies of different equipments in the plant. Also, we are doing performance calculation for the available yield and expected yield. Then the availability factors, which is like your technical availability, your functional availability of each equipment within the PV plant. So that is also part of the solution which we have provided. Now, if I'll just take the example of this architecture, wherein what are the automation control and SCADA piece we provide in a solar. So if you see On the right side, if you start from the bottom, there is the field side of it. And this is a typical solar PV where you have your string of PV inverters and then you have your combiner box. And then we have this inverter which is converting your single line DC into three-phase AC, which is your three-phase AC current. And then it is having an MV transformer, and then it goes to the substation side where it is stepped up. So you have your HV transformer, and then you have your point of connection with the grid. So we call this layer as the data collector layer, where our system interface with different equipments and devices, be it inverters, be it your power quality meters, be it your combiner boxes. And then we have the open platform. So we can communicate over different communication protocols over Modbus TCP IP. And in this particular project, all the communication from the field side from inverters were happening over Modbus TCP IP protocol. And also we were doing the substation control, in which we were interfacing with IEDs and switch gears over IEC 61850 MMS protocol. So that is what we are using. And then the third interface which we were doing is from the grid operator side, where we were interfacing over IEC 608705104 protocol. So this is the data collector layer in the field side, and here you will be having your inverter blocks and interfacing with the fiber optic ring network. And then you have the main control room where the PPC, which is the power plant controller, resides, which is the heart of any solar PV plant. And here we are doing all the control logics, including your active power control, where we are doing, maintaining based on the availability of each inverter and the power generation availability of the solar irradiance. We are defining the active power set point and also doing the ramp down and ramp up command from the PPC, so that we can meet the actual demand which is available from the grid. So that is the key control algorithms which are available. Then similarly, we are doing the reactive power control or voltage control. Then we have the frequency control. So we have doing at the point of connection with the grid, you have to maintain the grid frequency. So that is what we define in the megawatt control loop which we have, and also the megavar, which is the voltage control. So these are the controls which we are doing. And then since it is only solar, not backed up by the battery energy storage, so we also do a reserve control mechanism, in which we run the plant at a reserve, where we maintain a reserve of say 5 megawatt or 10 megawatt based on the plant size. And in case there is a sudden fluctuation, maybe your solar is down, there is a cloudiness, or there is a string which has gone broken. So this, with the help of this reserve control algorithm, we can maintain the grid requirement, so that we maintain the frequency and voltage and make the grid stable. So that is basically the key for any solar PV plant, where how you handle the intermittency on the solar side of it. So these are the control algorithms, and Lodestone is also talking with us to integrate this with battery energy storage going forward, where they are also discussing on PV smoothing, where we are going to use the excess solar power maybe to charge your battery energy storage. Right now we are putting a curtailment logic, and we are using the curtailment for the inverters. So that also we have done in this project. And at each field's plant site, there is a SCADA, which is the site SCADA, where you are seeing all your aggregated dashboards for your different inverters. You can start with a whole plant view and can go deep dive into an individual unit like inverter or weather monitoring station, and maybe an IED or a switch gear. So we are doing all the dashboard and data analysis on this. So this is like your one site over here. And then if you go on the top, we are doing the fleet-wise monitoring. So in this particular project, there were 5 solar PV plants. So we were doing the PPC and SCADA for individual site, and then we were integrating it and putting it as a remote operation center, which is in the Auckland, which is their head office. So that was our scope. And once we are getting all the data from the sites into our centralized, SCADA sitting in the head office, we are doing the data analytics on the top of that, in which we are doing all the KPIs and all the availability data, which caters to the GATS reporting. which is generation availability data system reporting, and that is NERC compliant, which is the the national energy regulatory compliance, which is used for reporting the availability data of your plant equipments. So that is also we are doing in this project. And now let me just show you this, and I think this might be a known picture for the people who are from the automation and from the control system background. This is our typical system architecture, which we say how the hardware and software and networking is deployed. So you can see there are 5 plants. Each plant is connected over the network, and we are providing the PPC and SCADA, of course, with the HMIs and servers like that. And then all the 5 plants are connected centrally, and this is over the remote using the cloud network, which is in the head office. We have our centralized SCADA server, which is doing all the data analytics and performance calculation for us. So that is how this whole plant is running, and going forward, they are going to integrate 3 new plants also. So now, if I explain some of the challenges which customer was facing, and then how our solution helps in terms of mitigating those and providing the PPC and SCADA. So first four I touched in the previous slide also, which is more related to the solar intermittency and how the PPC is handling the different controls which are related to, say, first the AGC controls, which is your automatic generation control. So whatever set point or the demand is coming, how you are going to manage the demand and make it equivalent with your power source, which is your inverters. So for this project, there were 5 inverter blocks, and each inverter block having 1 megawatt capacity, and it was a central inverter configuration. So we were receiving the set point, and we were dispatching the set point to the energy assets, which is the PV inverter, and also taking care of the intermittency. Making it, matching the demand with the availability of the power generation source. And second is how we are doing the active power and reactive power controls, and also doing the frequency control. So we have the fast frequency control algorithm, which caters to your megawatt set point. And also we are doing the voltage control, which is the megawatt control, which is a reactive power control. And last one is on the SCADA piece, which I explained, where we can do a lot of data analysis and do the dashboard and performance calculation for your plant. So these are some of the screens from the project which we have defined, and of course we have around 35 dashboards which are being designed, in which the plant operator can actually visualize the whole plant in terms of different assets which are running, and also they can do remote operations, giving a start stop command or giving a ramp up ramp down command sitting from the control room. So this is purely a manless plant. There are zero operators inside the plant, and everything is being run remotely from the remote operation center at the head office. So as you can see, we can do dashboards for inverters, for switch gears, for weather monitoring station. So there was a Kip and Zonen weather monitoring station, and we are doing all the dashboards here. In fact, the operator can also do any kind of, if there is a fluctuation or variation in the solar, how you are going to do your PQ controls, which is your active power control and reactive power controls. That also is being available on the operator dashboard. So no one is required to actually go on the site and do any physical work at the site, and also they can plan their activities based on the predictive model which is running here, where they can do the plant maintenance. So that is what we are showing out here. And then you can see the single line diagram for your electrical side, where you have your electrical intelligent devices. And also we are doing remote monitoring for different, so we have a map view where you can actually log in and see where your asset is actually located. So that is what we are doing on the dashboards. And just to summarize here,
you have to finish in a minute.
Yeah. So we are basically providing this SCADA and PPC for the 5 sites, and as I said, we are going to integrate future sites also and integrate the best technology, where we will be moving to the hybrid PPC architecture. So we are going to have the customer or the operator is going to have the big data access. He can access all the data in the plant in one single system. So it's like opening the black box and having the data available. Then also doing the optimized grid interface control. That is the key for the PPC solutions which we are providing. And then we are doing all the data analytics on the top of that and increasing the availability and asset visualization. And also doing, because this is kind of a standard algorithms which are available in our PPC. So the turnout time to the customer is also very less when we deploy and do a project of this scale. So with this, they are able to deploy a reliable, affordable, and sustainable power generation in their plant, which is helping them to reduce their cost and improve the efficiency of their power
Please
plant.
finish.
Yeah, and then they're also able to, meet their decarbonization target, which they are doing by deploying such plants. So this is not only the story of Lodestone Energy. We are doing similar projects globally in different world areas, and I'm more connected on the Asia side of it, where we have been working with several power utility customers and doing these solutions. So that's all from my side. Thank you for listening to me.
Thank you so much, Shubhi. It was a very nice presentation in terms of a case study of a large scale solar plant, which you presented critical aspects related to the maintaining the stability, automation, and challenges. We'll have the question answer at the end. I request my co-chair to invite the next speaker, please.
Now I invite Mr. Satish Kumar Sinha for his presentation. Mr. Satish Kumar Sinha is IIT Kharagpur graduate, and he did his master's and PhD in geophysics from University of Oklahoma. He worked for Shell Gas. He also worked for Reliance and worked for BP as geophysicist. Now he is working in RGIPT as HOD of Petroleum Engineering and Geoengineering. I request Mr. Professor Sinha for his presentation, and all the best for the presentation.
Thank you, Chair, for the nice introduction, and good morning to all of you. So, I have worked in seismic. That has been my domain. Seismic investigation, whether it's deep, subsurface, or recently we also started working on near subsurface with Maswa technique. But one of my students got interested in ground penetrating radar. And basically the difference here only is that in seismic we are dealing with acoustic, and here we are dealing with electromagnetics. And of course, here we are talking about two things. One is GPR, that is ground penetrating radar, and smart cities. Of course, probably you are aware about radar because you have seen all the time at airports all those revolving things which catches these flight locations. But in ground penetrating radar, basically what we are dealing with is very lower frequency electromagnetic waves, where we can detect architecture of the subsurface, and that is close about 10 meters or so. But in fact we can go even deeper if we do biostatic for different purposes. But for smart cities, basically what we are talking about is GPR, where we are looking at utilities antenna. Okay, and typically people do monostatic antenna with close to 300 to 400 megahertz antenna. So basically this is a presentation was made by Krishna Kumar Yadav, and I being his supervisor, so I am talking about this. And so let me, I think, go with this one. Yeah. So we'll talk about the smart cities and its goals, challenges in development of a smart city, GPR, and how it works. Then we'll talk about GPR signals and application, and one case study and advantages of GPR. Basically, I got interested in this GPR because where we are located in Rai Bareli, close to Jayas, in Jayas, close to Rai Bareli, or close to Lucknow. And Lucknow is a smart city. It's being made as a smart city, and also south of our campus. In further south we have Prayagraj, which is again being made as a smart city. So two smart cities coming around near our campus, and so but the thing is, we always kind of think about what is that a smart city mean. A smart city means different thing for different people, right? And so there is no universally accepted definition of a smart city. It means definitely different things to different people, and different from different country, and even within country, different city to different city. So basically, the conceptualization of a smart city varies from city to city and country to country, depending upon their level of development, willingness to change and reform, resources and aspirations of the city residents. A smart city would have a different connotation in India than, say, in Europe. Even in India, there is no one definition of a smart city. But definitely, as you can see, what a smart city should have is some form of a good infrastructure, or smart governance, a smart healthcare, building, mobility, a smart infrastructure, technology, energy, and a smart citizens. Okay, so that is what okay, so many gadgets. But challenges in developing this smart city, we have different geological conditions. So you may have where one smart city may have been on rocky areas, and one may be in a plain areas. So those geological conditions, there may be hard rock, there may be soft rock. Water management, some places may have underground water and some places do not. So how to develop that? Topography and land use, definitely connectivity challenges for those smart cities. Natural disaster may have, if you have coastal areas, it has different challenges than which are in the land. Energy harvesting and climate variability. Okay, you have temperatures changing from summer to winter. So what is ground penetrating radar? Basically, you have what I am showing here is I think, does this work? Yeah. No, it doesn't. So as you can see, this person is taking this GPR. It is basically a monostatic antenna which has one transmitter and one receiver, so that is going from point to point. And so if there is any point reflector, like you may have pipeline or you may have cable, so you see those diffraction hyperbola. And on your right, as you can see, there is the cart that is driven by this with this GPR, and you have a display on the top. At our institute, we have this GPR from GSSI, and not only monostatic, but we also have biostatic with variable frequencies. Okay, so basically, what in GPR, basically what you have is this dielectric constant that changes. So if you have dielectric contrast, and so you get reflections from there. So this is Maxwell equations that people use for electromagnetic wave propagation. So not an issue. Okay, so here is some typical frequency range that I'm giving here. So 1.5 gigahertz, maximum penetration depth is about half a meter. Nowadays, in fact, even people who want to do, let's say pillar and columns, and what the, their strengths and, if there is any cavity. So they use 2 gigahertz antenna. For 9 megahertz, depth can go to, 1 meter. For 400 megahertz, 4 meter and 276 meter. So as you can see that, lower frequencies goes to deeper depth. And of course, that is going to depend upon the geology of the area. Okay, that, that is very, very important to remember. Because, if you are doing some GPR in, permafrost region or, for glacier, studies, you can do with this 400 megahertz, and you can go, a kilometer deep. But if you are in plains where you have clays in the soil, so hardly you go to 5 to 10 meters. Biostatic antennas, you will see that most of them come below 100 megahertz. And those things can go deeper, 30, 40 meters, they can go. Smart cities, as you can see, if you want to build this older cities and a smart city, so what happens? You have so many different types of, utilities buried under the ground, okay? And typically you see those things that whenever construction is taking place, some pipelines, some, cables are broken, okay? So with this GPR technology, you can, map these things out, and, you can avoid this breaking. So there's one, yeah. So, of course, a smart city develop, you have subsurface geology that you can study, location of rebar or post-tension cables, utility conduit mapping, slab thickness, concrete cover. So all these things, even for, roads, people are, looking at, what kind of thickness, there has been. So what you see is, whenever you have some kind of, diffractor, so it makes a kind of hyperbola, okay? And so that is what you tend to, look at. For geological purposes, for beddings and all these things, it's a different thing, you can, of course, find out. But, for cables, conduits, you see all this hyperbola. And that is what, you try to figure out what they could be. So definitely, you also need to have some kind of a priori information. That's again limitation in this case. So this is another for transport infrastructure, roads and pavement inspection, bridge deck inspection, railway and subway maintenance. In fact, recently, if you remember, there was one incident that happened in Uttarakhand in the tunnel, and so people were trying to understand with GPR what those things are, concrete near the tunnel. So GPR was very helpful there too. Yeah, so tunnels and curves, foundation assessment. So all these things you can do with GPR. There are a lot of applications that you can think of with GPR. So basically, you have to think about the kind of frequency that you want to use. If it's shallower, and if it's if it's a very thin pipes. Less diameter pipes, then in that case, you want to have higher frequency. And if it's deeper, and if it's, then you want to have lower frequency antenna. Landfill monitoring, yeah, there's yet another application. So this is that case study that we did for Lucknow area. And as you can see, there is, these buildings all around. And then we were told that there are some sewer lines and, water lines that, where that is going, they did not have any map of this. And these are quite old ones. And so then we took those, our GPR GPR instrument, and two of my students, as you can see, they are walking along that road. And so we covered quite, 5 to 10 kilometers distances. And as you can see, in there were old sewer lines and water pipelines. They were existing, but people have built houses around there, encroachment and things like that has happened. And municipal corporation didn't have a clue about it. So you can use this GPR for a smart city development. Okay, so advantages of GPR, yeah, it is extremely accurate, depending upon frequencies. You may have centimeter resolution. It's quite fast, and it's non-destructive. You can do that in real time, non-intrusive, and of course you can store it easily and easy to operate, and it's quite safe. So that's all I have. And if you want to get in touch with me, you can always contact me. Yeah. All right. Thank you.
Thank you, Mr. Sinha, for finishing your presentation well in time. Thank you so much. You presented a smart way to develop a smart city. So,
Welcome, Mr. Meghasham. We are awaiting you for long. Anyhow, I'll just give a brief introduction of him. He's a mechanical engineer. He worked in CSR, National Aerospace Laboratory, and was involved in preparation of standard modules for carbon fiber. He is presently working with ONGC Energy Center, and he has a presentation on geothermal, I think. We welcome you and all the best for your presentation.
So good morning all of you. So India being blessed with wide topographies and hotspots, so it is very much ideal to harness renewable energy resources. So one such resource is geothermal energy that we have undertaken as ONGC Energy Center in 2021. Next slide wala kaun sa? Slide changing wala. Yeah. So one of the energy resources, renewable energy resources that ONGC Energy Center has undertaken is geothermal energy. Since 2021, we have been working on it. We have signed an agreement with MOU with UT Ladakh and Ladakh Autonomous Hill Development Council. So as we know, geothermal is a type of clean, renewable, sustainable and environmental friendly energy that is stored in the form of heat beneath the Earth's surface. Obviously, it's available 24/7. That's why it has got the most advantage of harnessing out of all resources. Mainly the form of energy that comes from the radioactive decay that is available in the form of heat, especially the magmatic rocks, it's semi-molten, and slowly they keep emanating the heat to the upper layers of the earth. So whatever heat that is stored in the form, it has got high pressure. So because of the intensity of pressure, the water that gets vaporized and gushes out of the topsoil. That is the way the energy gets harnessed. Over the period of time, since 3 decades, GSI had explored, they took the initiative of geothermal energy, and they had identified almost 6 to 7 main provinces across India. And they had identified more than 300 hot springs, mainly in the Himalayan belt, Aravalis, West Coast, Cambay Basin, Sonata, Godavari, and Mahanadi Basin. So overall, geothermal has got almost 10 gigawatt of potential, out of which most promising is Puga Valley, that's in Ladakh. As you know, Ladakh is one of the most remote regions in India, and even it's strategically more important since it shares its border with or friends of the neighboring countries like Pakistan and China. So there are no fossil fuels available as such over there, and rivers get frozen in the winter. But in summer the river gets silting, and it's a bottleneck to the turbines. And the dry cold climate uh, can go up to minus 30 degrees centigrade in the winter, and obviously the altitude is only 3,500 meters above mean sea level. Likewise, the atmospheric pressure is like 40% less than the normal atmosphere. And Leh, there's the largest district, and population is quite like 1,47,000, and Kargil is the second largest district. Leh town itself has about 75,000, remaining population it's distributed across 112 villages and hamlets. So this is a brief introduction of Ladakh. And coming to the point, the peak summer power demand in entire Ladakh is approximately 115 megawatts, and current installed capacity is 71. And out of which 13.5 megawatt, 4 megawatt comes from a Stakna hydroelectric plant. Uh, and especially during winter, the dam, the power station gets shut down. So there is no much electricity supply during the winter, and it's a bit challenging. So during this lock period, main source of supply is only the diesel generator. But conversion from diesel generator is also an expensive method. All the fuel that has to be imported from the neighboring states, especially from Chandigarh and Delhi, has to be airlifted. And the subsidized cost of power over there is like 7.5 rupees per unit. So once the tourists got attracted to the the ecosystem of Ladakh, there's a sporadic change in the culture of the people. Uh, the tourism lifestyle, everything got adopted from the outer world. Um, you know, because of that, power revenue also met by importing fossil fuels from the outside state. 8,000 liters of diesel is sufficient power for a day's consumption in Ladakh, and fuel imported from other states. And 3 lakh liters of diesel is burnt over there, and 13 megawatt for the 13 megawatt power consumption. And 120 million is being spent in order to consume 3 lakh liters, and even 28,000 metric ton of carbon dioxide is being produced over there. So because of that, Himalayan glaciers and Gangotri, that gets receding every year, and on an average it's 18 meter per year. So coming to the point, this is a distribution of hot springs and the potential in Himalayan belt. Like Puga, Chumata, and Nubra are the most highest potential. Overall, it's 30 to 70 megawatt is the potential. And astrobiological research is being conducted over there by different bodies. So the sample is being collected and tested, and more research is being conducted over there. So Puga Valley, it's situated 180 kilometers from Leh. Area is 5 square kilometer. GSI had explored 34 boreholes, and out of 8 of which are flowing and rest were abandoned because one of the other reasons, bloat and others, corrosion. Maximum they could go was up to 385 meters, and like steam content was approximately 10%, 10 to 15%. And reservoir temperature was estimated to be 220 to 250 degrees centigrade, and discharge was 120 and 130, and surface it comes down to 80 degrees Celsius in that particular pressure, and maximum discharge pressure was 2 to 3 bar. So this is our plan. Once we generate electricity, it can be transported up to the city of Leh, like 180 kilometers through insulated pipe. After utilizing the for like other applications other than electricity byproducts, it can be reused and sent back to the earth. So in that way, you can do the closed loop cycle. This is a surface manifestation of hot spring, and the left side we can see the distribution of boreholes that was plotted by Geological Survey of India. This was a recent clip captured in Chumatang. We had a recent visit over there. Yeah. And you can see the temperature, highest temperature that GSA had recorded 130 degrees centigrade at the depth of like 60 meter, and further deep borehole was like up to 280 meter, it was 127 degrees centigrade. Further deep they couldn't explore because of technological failure. So harnessing, it can be categorized in three based on the temperature what we are going to achieve in the discharge and reservoir. Like if the steam outlet is 220 degree, then we can establish a dry steam plant. If there's a mixture of both water as well as steam, then we can flash and convert and produce a better efficient, that's flash steam plant if it exceeds 182 degrees centigrade. And if the output is only hot water, then we can establish a binary plant where we use organic fluid which has got a lesser boiling point than water. Say ammonia, it has got minus 40 degrees centigrade. Then it will vaporize the geothermal water and get electricity. You can produce. This is a closed loop, as I explained before. So we can see sulfur and borax deposits across the the valley, alluvial soil, topsoil. This is a distribution, and these are a few challenges what I wanted to mention. Working seasons limited only May to October. That's 6 months hardly, and even working in the late evenings, it's quite challenging. And rest of the time it's landlocked. So it falls in Chantang Wildlife Sanctuary and environmental sensitive to flora and fauna of that particular area. You have to procure almost all the clearances, and to get that is very good challenging. And transportation, you have to come across the different terrains, undulated topography, and stability of land while drilling is also a bit challenging. Recently, in even media, it's been highlighted. Chumatang and Puga earthquakes frequently happen. Tibetan plates. All are the factors that all are concerns that disturb the geological plates. And the photo that you can see, this is a shallow depth high steam that we had encountered in the recent campaign last year. Yeah. So owing to the design, we proper well design and surface facility design, everything has to be very much planned. Uh, and access to drilling location, we need to cross the nala, and proper logistics has to be arranged. And there's a cold spring, and it's a local source for the the villages over there. All these things we have to keep in the mind, to establish the plant. And these are the byproducts of geothermal for direct utilization. It's depends on what temperature we get as output. For the low enthalpy, it can be used for the space heating. If the temperature falls between 60 to 70 to 120 or something. So the photo that we can see, Blue Lagoon, Iceland, geothermal spa, that is quite popular. Even Ladakh has got potential similar to the Iceland. It's very much compared. So that gives a boost to the tourism and hospitality, self-employment, and the rest of the sectors. So this is the crux of the project. What possible outcomes of the project? Mainly to provide electricity and provide as a base load, especially during the winter when the rivers get frozen and hydropower stations are shut. And obviously it can run 24 hours a day at an average of 340 days, giving a high capacity factor of over 90%. So even installation of 20 megawatt geothermal plant at Puga would save 3 million liters of diesel burnt annually at a cost approximately of $2 million US. And that would eliminate the need of traditional kerosene, burning bukharis and gas operated heaters. So finally, eliminate some 28,000 metric ton of carbon dioxide each year, an additional 2 million liters of diesel used by Indian Army for power generation that might be saved, and creating carbon neutral Ladakh and protect the pristine ecosystem of Himalayas and glaciers. Thank you all for the time, for my time. Thank you.
Thank you, Mr. Khandige, for finishing the presentation well within time. You covered a very beautiful aspect of source of energy beneath the earth. Covered in a very beautiful way. Well, due to paucity of time and already we have crossed the session time, so the request from organizer is to not to have the question answer session, and you can, if query if you have, you can directly pose to the speakers who are available here after the conclusion of the session.